All right, we're going to begin section 15.8 in this video, which is the divergence theorem. So first I'll just give kind of an explanation of what's going on with the divergence theorem before I actually state the theorem itself. So the divergence theorem relates a triple integral over a three-dimensional solid to a surface integral over the surface that is the boundary of the three-dimensional solid. So it's similar to Green's theorem and Stokes' theorem. In Green's theorem, we have a two-dimensional region R, which has a boundary curve, and we relate a line integral over the boundary curve to a double integral over the region R. For Stokes' theorem, we have a three-dimensional surface S, and we relate a surface integral over S to a line integral over the boundary curve C of S. And then the divergence theorem is doing a similar thing, but now we're looking at a three-dimensional solid. And a three-dimensional solid is going to have an inherent boundary surface. So now we're going to do relate a triple integral over the three-dimensional solid to a surface integral over the surface that bounds that three-dimensional solid. All right, so let D be a simple solid region and simple solid regions are just the regions that over which we were integrating in chapter 14 when we were doing triple integrals. So then that's to include spherical coordinates, cylindrical coordinates, change of variables. We didn't do any change of variables, extensive change of variables problems for triple integrals, but spherical coordinates, cylindrical coordinates are a form of change of variables, and then rectangular coordinates, of course, as well. So let D be a simple solid region, and let S be the boundary surface of D with positive outward orientation. So whenever we have a solid, so imagine, say, your textbook, for instance. Your textbook is a three-dimensional solid. The cover of your textbook would be like the surface. If you just imagine just the outside of the textbook, that's the inherent boundary surface. Or say if you take a golf ball, for instance, then the golf ball is a three-dimensional solid, but the outside of that golf ball, the part that you actually see, that's the surface. So any three-dimensional solid has an inherent boundary surface. So that's what we're talking about here when we say the boundary surface of the solid D. So let F be a vector field whose components have continuous partial derivatives on D. then the surface integral over S of f dot n ds equals the triple integral over d of the divergence of f dv. So the exercises that we do in 15.8 for the most part are going to be just us kind of revisiting our skills to set up and evaluate a triple integral. Of course, we'll have to actually take the divergence as well, but that will be fairly easy. And then the triple integral part, the setup, the bounds of the triple integral part is what we're going to have to go back and make sure we remember how to do. All right, so one other thing worth mentioning is, since we're at the end of chapter 15, pages 1063, 1064, give an overview of all the different formulas that we use in this chapter. So those are good pages to go over and read to make sure you understand the difference between the formulas and know all the different formulas that we're covering. All right, so we're going to now do an example. So the example we're doing is on page, let's see, we're on page 1060. We're going to do number 11. And just like Green's theorem and Stokes' theorem, the divergence theorem is just saying if you're told to evaluate this and it's easier to do that, you can do that, or vice versa. If you're told to evaluate this and it's easier to do that, then you can do the surface integral instead of the triple integral. It goes either way. Now, it's a rare occasion that you're told to evaluate this right-hand side by doing the left-hand side, but it can be done though. All right, so now with number 11, our directions say in exercises 9 through 23, use the divergence theorem to compute the surface integral, of f dot n ds, where n is the normal to sigma that is directed outward. All right, so we're told to compute this using the divergence theorem, which means we have to use the triple integral. We're not given an option in this question which one to do. All right, so our vector field for 11 is f of xyz equals xyz. And they say that sigma is the boundary of the solid region in the first octant that is inside the cylinder x squared plus y squared equals 1. And between the planes, z equals 0 and z equals 1. All right, so I'm going to sketch our surface just so we can talk about what this problem would entail if we were to evaluate the left-hand side directly, which is not what we're going to do because we weren't told to do. We were told to use the divergence theorem. So just so we can see the usefulness of the divergence theorem though. All right, so we're looking at the cylinder, the portion of the cylinder. All right, and this entire thing would be filled in because we're looking at the three-dimensional solid. So now if we were trying to evaluate this surface integral, then the surface would be the boundary of the three-dimensional solid. So we would have this plane at the top, the plane at the bottom, the plane in the xz plane, the plane in the yz plane, and then this portion of the cylinder here. So we would have, and I'm going to sketch, well, we're told this in the problem, we won't need these vectors for what approach we're using, but I'm going to sketch normal vectors just so we can kind of see what's going on here. So this normal vector right here is coming from the YZ plane and going backwards and then we'd have a normal vector going directly up. We would have a normal vector going directly down from that bottom plane. We would have a normal vector going to the left from the XZ plane. And then we'd have a normal vector on the cylinder. Basically go something like this. All right, so we would have, how many surfaces? I say 5 different surfaces. So we would have to evaluate this surface integral over each one of those 5 surfaces and then add those 5 surface integrals. So this would be a lengthy problem if we were to just evaluate this directly. Now let's look at using the divergence theorem instead. So by the divergence theorem, what we're going to do is we just need to be able to set up a triple integral over this. And we know how to do that when we think of setting up a triple integral. Our bounds, the way we do that is we have top, bottom, and then our quote unquote sides. So we need to look at things that way instead. So first, let's find the divergence of F. And remember how we compute divergence. Take the partial of m with respect to x, the partial of n with respect to y, and the partial of p with respect to z. So these are m, n, and p. And this is partial of m with respect to x, plus the partial of n with respect to y, plus the partial of p with respect to z, which is 1 plus 1 plus 1 for us. 1 plus 1 plus 1. So we get our divergence is 3. Then let's go back to how we set up things for triple integrals. We will write finding our bounds. We will look at what is the top. And that's just, this is also dependent on which way we choose to look at this. So the fact I'm doing top and bottom is saying I'm going to take this thing and project it down into the XY plane. You could, if you wanted to, project it to the left into the XZ plane or back into the YZ plane. Any one of those is fine. So on the top here is, what was that, z equals 1, I think. Yes, z equals 1. The bottom was z equals 0. And the sides were given by the cylinder, the XZ plane, excuse me, and the YZ plane. So in the cylinder had radius 1 as well, I think. Yes, okay, so x squared plus y squared equals 1. So sides so here we would say intersection of x squared plus y squared equals 1, y equals 0, and x equals 0. So x equals 0, the YZ plane, and then y equals 0. So we intersect those 3 things. X equals 0. Y equals 0. All right, so now we always would sketch the sides part and then set everything up from there. So our sides will look like this. And then we write down our region D. So D is the set of points X, Y, Z, such that, and we can do this, we can switch our coordinate system if we want to, but it's not necessary. So if we wanted to say do cylindrical, of course we could switch and do that. Actually, before I do this, well, this is what we would do, but I'm not going to do that for this problem because our divergence was just a constant. So we can do this a lot easier by just first, let's just write down what our integral is. The triple integral, and we'll just leave d right there because we don't have it written out right now. Our integrand is just 3 dv. So this really is just 3 times the volume of d. So I was going to go through and write out what d is and set up the triple integral like we usually would. The d would give us our bounds here. But then I remembered that our integrand is just a constant. So we pull the constant out and we have the triple integral over d of 1 dv, which is just the volume of d. So now we can just use our knowledge of geometry and the volume of the cylinder that we had drawn on the previous page. So 3 times, what is the volume of this thing? So the volume of a right cylinder is pi r squared times the height. So we have our radius here was 1. So this is going to be pi times 1 squared times our height on that cylinder was also 1. So times 1. But then that will be the entire cylinder. We have a quarter of the cylinder. So we take that and divide it by 4. So we get 3 pi over 4. And we don't have to worry about setting up those bounds because we just use our knowledge of geometry and our knowledge of triple integrals to do it that way instead. All right, so I'll stop this video here and then we'll continue with section 15.8 in our next video.